Hello everyone. In this video, we'll be discussing about the derivation of capacitance between two coaxial conducting cones in spherical system, which is the example of solution to Laplace equation for one-dimensional potential function. Now here we are considering two cones which are coaxial. So this is the first cone whose axis is the same as the second cone. The two cones have the included angle, which is theta1 and theta2 respectively. This angle theta is the elevation angle in spherical system. So we will be following spherical system of coordinates to find the potential function between these two conducting cones, and also we will be extracting the capacitance between the two conducting cones. One important thing to be noted here is the two cones should not touch each other, because these two conducting cones should be maintained at two different potentials. If the two cones touch each other, the conductors touching each other will maintain the potential to be same. In that case, there will not be any difference in potential existing between the two cones. So in order to have difference in potential between the two cones, there should be at least infinitely small gap between the two. And here we are considering the angle for the first cone is theta1 and the angle for the second cone is theta2. Between these two, the potential is going to be a function of theta. So in this case, we are going to consider the region between the two is filled with the dielectric constant, and thereby the region is free of charges, which enables us to apply the Laplace equation for solving for the potential between the two conducting cones. We will be solving the Laplace equation to get the potential, and from potential function we can find electric field intensity as negative gradient of potential, and from electric field intensity we can find flux density in terms of the dielectric materials constant, and from flux density we can find charge by using the Gauss law. And capacitance can be estimated as the ratio of charge stored in any one of the plates to the difference in potential between the two plates. We will go through the steps one by one for a special case of this with a specific value of theta1 and theta2 to proceed to get the capacitance expression for this case. So this is the general case where the angle of the inner cone is at theta1, angle of the outer cone is at theta2. We will be considering a special case of this where the angle of the inner cone is alpha and the outer one is at an angle of 90 degrees or pi by 2. So if the outer cone is at an angle of 90 degrees, that will make the cone to be a flat circular disc at the bottom. So this is a flat circular disc at the bottom, which is the cone with the special case of angle 90 degrees or pi by 2. And the inner one is at an angle of alpha. Now between these two cones, the region is filled with the dielectric material of dielectric constant epsilon r. And between these two, potential is going to vary with respect to angle theta. That is, V is a function of the elevation angle theta. Now we will be considering the Laplace equation and consider the boundary conditions also. We will be providing supply to these two plates, like the plate with an angle of alpha is connected to positive terminal of the supply voltage V0, and this circular disc, which is having an angle pi by 2, is connected to the negative of the supply voltage, which is also grounded. Now we can write the boundary conditions for this case. For angle theta is equal to alpha, potential V is V0, and an angle of theta is equal to pi by 2, potential V is 0. Now taking these two boundary conditions, we will be solving for the Laplace equation to get V of theta. So del square V equals to 0 talks about the Laplace equation. We have to write this del square V function in spherical system of coordinates. This is the expression for del square V in spherical system of coordinates. Here in this case, V is a function of only theta, and thereby the differentiations with respect to r and phi will be eliminated. We will have the differentiation with respect to theta as non-zero. Only this term will be there in del square V, which is equal to 0. Thereby, we can start doing the integration to get the potential V, which is a function of theta. Now, in this case, this term 1 by r squared sine theta can be multiplied with the right-hand side. It has to be brought to the right-hand side, and which will make the term in the right-hand side 0. You'll have differential element d by d theta into sine theta of dv by d theta equals to 0. Now we can integrate with respect to theta to remove the two differentiations with respect to theta. First integration we will perform, and that is going to remove this differentiation d by d theta. The left hand side will be sine theta dv by d theta, and the right hand side integration of 0 is 0 plus integration constant c1. So you'll get sine theta dv by d theta equals to integration of 0 is 0 plus constant c1. Now this sine theta has to be taken to the right hand side. So this will make dv by d theta equals c1 by sine theta. Now one more integration with respect to theta will remove this differentiation to give the potential function v. So one more integration with respect to theta will give v in the left hand side. In the right hand side, c1 by sine theta has to be integrated with respect to theta. C1 is constant. We need to know what is the formula for 1 by sine theta d theta integration. So integration of 1 by sine theta d theta is natural logarithm of tan of theta by 2. This is the formula for integration of 1 by sine theta d theta. Now, instead of 1 by sine theta d theta integration, we will be writing this. So thereby, v will be integration of this plus integration constant c2. Since no limits are provided, we have to write integration constants after every integration. Now, v is equal to c1 into logarithm of tan theta by 2 plus c2. This is the potential function v, which is having a variable only theta. Now, we have to find the constant c1 and c2 by applying the boundary conditions. We have to apply the boundary conditions for our special case considered, which talks about theta at angle theta is equal to phi, potential v is v naught, and at angle theta is equal to pi by 2, potential is 0. Now let us apply the first boundary condition to this expression for v. We will get v naught equals to c1 into logarithm tan alpha by 2 plus c2. When we apply the second boundary condition, we will get 0 equals to c1 into logarithm of tan of pi by 2 by 2. That will become pi by 4 plus c2. Now we have to find what is this value, natural logarithm of tan pi by 4. You can take the calculator and estimate this. This is going to be equal to 0. So now when c1 and the multiplication factor is 0 plus c2 equals to 0, which will give c2 equals to 0. Now we can take c2 equals to 0 in this equation, and v naught will be equal to c1 logarithm of tan alpha by 2. From this, we can find c1 as v naught by logarithm of tan alpha by 2. Now we have c2, c1. We can apply these two constants in this expression for v to get potential v as a function of theta. So applying this c2 and c1 in the expression for v, we will get v of theta as here. Now we have to estimate electric field intensity vector, which is the negative gradient of potential. This is the negative gradient of potential in spherical system of coordinates. We know v is a function of only theta. So differentiation of v with respect to r and differentiation of v with respect to phi will be 0. Only the second term is going to be left, and we have to do differentiation with respect to theta. You know this constants, and you have logarithm of tan theta by 2. So now this has to be differentiated with respect to theta. We can write the formula for differentiation. We know 1 by sine theta integration is going to give logarithm of tan theta by 2. Now, if I want to differentiate this logarithm of tan theta by 2, which is available over here, if I differentiate this with respect to theta, that is going to give back 1 by sine theta. So this differentiation of logarithm of tan theta by 2 can be written as 1 by sine theta. Now, the constants we can write in multiplication as it is. That is, this minus 1 by r is there in the formula, and v naught by logarithm tan alpha by 2 is the constant. Now, differentiation of logarithm of tan theta by 2 is going to be 1 by sine theta and a theta cap. This has to be the electric field intensity vector E, and the unit is volt per meter. Now from this, we can estimate the flux density as epsilon naught epsilon r times E vector. Multiplying that will give D vector. Now here there is a negative sign. Now this negative sign can be brought to the denominator. When we try to write this negative sign to the denominator, I will write in the denominator 1 by minus logarithm tan alpha by 2 is there. So this negative logarithm can be brought to this angle. So I can write this as minus 1 by logarithm tan alpha by 2 inverse. Now this inverse can be written as 1 by logarithm of 1 by tan alpha by 2. Now this 1 by tan can be written as cot. So thereby we will be getting this as 1 by logarithm cot alpha by 2. So this is going to be here in the denominator. So this negative sign, when we bring it to the denominator for logarithm of tan alpha by 2, we will get logarithm of cot alpha by 2 in the denominator. So thereby the expression for d vector is epsilon naught epsilon r v naught by r sine theta ln cot alpha by 2 in the direction a theta with the unit coulomb per meter square. Now with this d vector, we will be finding the charge. So the charge q can be estimated as surface integration of d over the area. Now to find the area of the cone, we have to consider the cone's radius starts from R0 to R1. Because there should be an infinitely small gap between the two cones, this radius should not start at 0. So the limits for R is R0 to R1, and the limits for theta is the entire 360 degree for this cone. For the variation of R and phi, the component of ds vector is theta component. So the variable for integration will be r sine theta dr d phi. This is the ds vector. Now you have d vector. We have to take dot product of this d vector and ds vector to get the charge enclosed. So multiplying these two components, d vector multiplied with ds vector, we have to do the multiplication and get the integration done. So the constants other than r and phi, the variables can be taken outside of the integration. So this r sine theta can be cancelled. Epsilon r v naught by logarithm of cot alpha by 2. This is constant. Now integration is dr d phi, where r limit is r0 to r1 and phi limit is 0 to 2 pi. This is going to give epsilon r v naught by logarithm of cot alpha by 2 into integration dr is r0 to r1, integration d phi is phi 0 to 2 pi. So thereby you will get epsilon r v naught r1 minus r0 into 2 pi divided by logarithm of cot alpha by 2. So this is the charge enclosed. So you can find the charge enclosed by performing integration, which is the expression given over here in the units of coulombs. Now we need to find the capacitive effect. So we have one conical plate which is at an angle of pi by 2, which becomes a circular disc. Another conical plate is an angle of alpha. Now there is an infinitely small gap between the two plates. Thereby the radius of this cone starts from R0 to R1. This enables there is an infinitely small gap between the two conducting cones to provide for difference in potential between the two plates, and that is going to give V, which is a function of theta. Now one plate is at positive V naught, another is at 0 potential. So the difference in potential between the two has to be found to find the capacitance. Charge is given by this expression. Difference in potential is V naught minus 0, which is going to be V naught. So Q by V naught will cancel this V naught. Thereby, we will get the capacitance expression for this case of two coaxial conducting cones is 2 pi epsilon naught epsilon r1 minus r0 divided by natural logarithm of cot alpha by 2, where the unit of capacitance is farads. This expression for capacitance is obtained only for this special case where one cone is at an angle of pi by 2, which becomes a circular disc. Another cone is at an angle of alpha. For other values of angles, the corresponding potential function will differ, and the charge enclosed also will be differing, and the capacitance also will be differing. This expression for capacitance is specific for the special case considered. I hope you have understood this derivation. Thanks for watching the video.